This is Paul again. We're ready to start rotating and reflecting some vectors in the plane. In the previous script, I showed you a handful of useful functions. I put those all into a script called 1.2L vectorlibrary.r, and all you have to do is use this source command in R, and you have access to all of those when running one of your own scripts. I've done the usual narrow margin setup for our screen, and we're ready to get going with rotation matrices. Remember that we have defined cos with a capital C and sine with a capital S so that we can specify our angle in degrees, and we've also defined A37 to be the smallest angle in a 3, 4, 5 right triangle. So if I want to rotate the first standard basis vector through 37 degrees, I turn it into a vector whose first component is the cosine of A37, that is 4/5, whose second component is the sine, namely 3/5. There's 0.8 and 0.6. The second standard basis vector is going to rotate so that it has a negative first component, a positive second component. There's the second basis vector, and the easiest way to see that we've got this right is to display those two vectors. So we'll set up a plot with some axes on it. Show the first standard basis vector, and in red the result of rotating it, the second standard basis vector, and again in red the result of rotating it. Clearly we figured out how to rotate the two standard basis vectors counterclockwise through 37 degrees, and once we know what a linear transformation does to the standard basis vectors, we know everything. We just bind those together into a matrix, and the matrix ROT37 will rotate any vector through 37 degrees. Let's try this out by taking our vectors C1 and C2, the red vectors, and rotating them through another 37 degrees to get RC1 and RC2. There's another 37 degrees applied to the first red vector and to the second red vector. And not too surprisingly, if we ask for the angle between the first blue vector and the first standard basis vector, we get something that is, for all intents and purposes, 74 degrees, twice 37 degrees. We've actually come up with a rather clever way of adding angles. To add two angles, we just rotate successively through the two angles and see what the result is. You're going to be able to use this idea in your own problem solving to rederive the addition formulas for the sine and cosine function. Let's automate this all by writing a function to define a rotation matrix. All we need is the counterclockwise angle of rotation. Let's call that A. The first column is the cosine of A and the sine of A. The second column is the sine of A and the cosine of A. And we need to specify the 2 so that R will know we want a matrix with 2 rows in it. Let's check that this works by applying it to the angle A37. And we get precisely what we want. First column is 0.8, 0.6. The second, minus 0.6 and 0.8. Now let's check our idea that when we do two successive rotations, angles add. We'll make rotation matrices for 24 degrees and 36 degrees. We will multiply these two matrices together, and we will also calculate the rotation matrix for 60 degrees. And on discovering that we've constructed exactly the same matrix by both methods, we know that our conjecture was correct. When you form the composition of two rotations, the the angles add. If I calculate the inverse of a rotation matrix, which I can do by using the solve function, I get another rotation matrix. Now the minus sign is in the lower left-hand corner. Let's see what the geometrical effect is if we apply this to the two standard basis vectors. We rotate them clockwise through 37 degrees. And if you look at that inverse matrix, you'll see the only change is that the minus sign is in the lower left-hand corner. This is the transpose of the matrix for a counterclockwise rotation through 37 degrees. This is a general result. The inverse of a rotation matrix is the same as its transpose. I can check that explicitly by applying the transpose function little t to rot 37. For any rotation, the determinant is +1. The reason for that is that it rotates the unit square into another square with exactly the same area. And the fact that the area doesn't change means the magnitude of the determinant has to be 1. Now let's look at reflection matrices. We'll clear the plot again and set up a matrix that reflects in a line that makes some angle A above the x-axis. The way you create this matrix is by using the cosine and sine of twice that angle. Exactly why you need twice the angle will become apparent in a minute. So here we've got a function that creates a reflection matrix. Let's choose A equals 20 degrees and create that matrix. We'll call it F20. Since reflection begins with an R, just the same way rotation does, we'll use the first distinctive consonant in reflection, namely the F. Now I want to show you this line that makes a 20-degree angle. The way you draw a line in R is by specifying its y-intercept and its slope. So the line we want has a y-intercept of 0. It goes through the origin, and its slope is the tangent of 20 degrees. I use tangent with a capital T because 20 is in degrees. And there is our line. Let me draw the first standard basis vector, and then let me plot the first column of the reflection matrix, and you see, sure enough, that first standard basis vector has been reflected in the black sloping line. Here's the second standard basis vector, which I have drawn in red, and the second column of the reflection matrix is the result of reflecting that in the same black reflection line. I can check the angle between the first standard basis vector and its image. The angle between function gives me 40. That's why we need in the matrix to have twice the angle of the reflection line, because each standard basis vector gets reflected through an angle that's twice that amount. What happens if you reflect twice? Well, you end up exactly where you started, don't you? And in terms of matrices, that means that the square of any reflection matrix should be the identity matrix. Sure enough, if I multiply F20 by itself, I get the 2 by 2 identity matrix. What about the determinant? Well, a reflection turns right-handed into left-handed, clockwise into counterclockwise, and that shows up in the fact that its determinant is a negative number. It's not +1, it's -1. That's one way of distinguishing a rotation matrix from a reflection matrix. Notice the reflection matrix is a symmetric matrix. It's identical to its transpose, as R will happily verify. Now for a really interesting result. The product of two reflections is a rotation. Basically, a reflection's an isometry, and the only isometries that hold the origin fixed are reflections and rotations. So we have to get either a reflection or a rotation, but since the determinant of a product is the product of determinants, we're going to get a matrix whose determinant is +1. That's going to be a rotation matrix. Let's try out a specific example. F35 reflects in a 35-degree line. And let's try first reflecting in the 20-degree line, then in the 35-degree line. Remember, the factor on the right tells us what happens first. Look at the product matrix. Well, the entries on the diagonal are equal. The entries on the off diagonal are equal and opposite. Sure enough, that's a rotation matrix, and we can figure out through what angle by just asking for the angle between the first column and the first standard basis vector. It's a rotation through 30 degrees. 30 degrees, conveniently, is twice the difference between 35 and 20 degrees. When you reflect successively in two lines, you get a rotation through an angle that is twice the angle between the two lines. If I do the reflections in the opposite order, remember matrix multiplication is not commutative, I get a different matrix, product 2. It's a rotation matrix. It looks very similar to the first one, doesn't it? But the minus sign's in a different position. That's because we got a rotation in the opposite sense. This is a rotation through minus 30 degrees. That is a clockwise rotation. Now let's clear the plot, set up our first reflection line and our second reflection line so we can watch exactly at what's going on. To figure out what happens to the first standard basis vector, we keep our eyes on the first column of the matrix. So there's our first standard basis vector drawn in blue. We reflect it in the red line by looking at the first column of F20. You can see it's been reflected in the red line. Now we reflect it in the green line. We know the effect of two reflections. That's the matrix that we called product. And when we reflect in the green line, we get that final red vector. The blue vector has been rotated through 30 degrees. Let's try things in the opposite order. First, reflect the first standard basis vector in the 35-degree line. Then when we reflect in the red line, we get the first column of the matrix we've been calling product 2. That's going to move it a whole long way. It's going to end up down below the horizontal axis, and we have succeeded in carrying out a clockwise rotation through 30 degrees. That's basically all there is to say about rotations and reflections, but you can have a lot of fun on the homework proving that the product of 3 reflections is a reflection, and the product of any number of reflections is either a reflection or rotation, which pretty much totally solves the problem of understanding the isometries of two-dimensional Euclidean geometry that hold the origin fixed.